Swayam Prabha. Digital India. Educated India.
In the context of neural networks. But there's a couple of problems with neural networks. The biggest problem is that neural networks require big data. They require a lot of data to be trained, and a lot of times they're very challenging to train. When you read the literature on neural networks, it's not uncommon to come across quotes like this one that says that suffering is a perfectly natural part of getting a neural network to work well. And it just reflects that neural networks are, a lot of times, they're highly non-trivial to train. Now, in physics, data come from the solutions of complex equations or from experiments, which are very difficult and very time-consuming generally. So data are expensive, and the focus of machine learning for physics should therefore be on making physical predictions based on small data, not big data, based on isolated measurements or isolated calculations. And this is what probabilistic modeling is actually good for. So deterministic neural networks, they simply cannot be used for problems with small data. But then there's another way to make predictions in machine learning, and that is probabilistic modeling. Probabilistic modeling is at the core of Bayesian machine learning, and we're going to see in a couple of minutes why we call it Bayesian machine learning. So probabilistic modeling can actually be done with neural networks if you convert a neural network, a deterministic neural network, into a Bayesian neural network, and you would do that by replacing all of the parameters of a neural network with random variables. So if you do that, then a prediction of a neural network becomes a random function, and if you sample enough of such random functions from the neural network, then you're going to get a distribution of functions like one shown on this graph here. So theta here describes collectively the many parameters of the neural network. So in probabilistic modeling, the goal is to condition this sort of distribution with data, the data points shown by the red dots here. So basically, what you want to do, you want to go from a distribution of functions like the one shown by the white curves here to the one like this. Okay? So the goal is to calculate this probability density here, where y is just a vector of the data points, the red data points here that you're going to be conditioning your distributions by. So this is done by using the Bayes theorem that relates p of theta y to the other probability distributions that are easier to calculate. And once you have this, of course, the goal is to make a prediction of the probability of a particular value, y star, at a particular point, x star, in the input space. And this probability is calculated by this integral here. Now, this is what makes Bayesian neural networks actually difficult to apply, because in a neural network, the number of parameters in this data is going to be very, very large. So these kind of integrals are going to be completely intractable. So this would be a problem if it wasn't for the work of this person by the name of Neal from the University of Toronto, who in the middle of the 90s showed that if you were to take a Bayesian neural network to the limit of an infinite number of hidden neurons here, so if you were to do that, then this Bayesian neural network becomes a Gaussian process. And for Gaussian processes, the integrals that I showed on the previous slide, they can be done analytically. And Bayesian machine learning becomes practical. What a Gaussian process is simply a normal distribution of random functions. So if you were to take this distribution and you were to cut it in this direction, then the distribution of values would be Gaussian. So Gaussian processes are completely determined by a mean function and a covariance function. And when you train a Gaussian process, the goal is to determine the conditional covariance function. In other words, the goal is to go from, again, something like this to something that's shown on the right side here. And this is done by assuming some mathematical form for the covariance function and varying the coefficients of this form to maximize p of y. What What you get this way is a predictive distribution, like the one shown on the right side here, whose mean, shown by the green curve, can be used to interpolate between isolated data points given by the red dots. And if you know how to construct Gaussian processes properly, this interpolation can be very efficient. To illustrate this, consider a potential energy surface that describes a chemical reaction of three atoms that typically looks like this. In order to construct such potential energy surfaces, one would typically calculate the potential energy of the system for a three-dimensional system, typically at between 1,000 and 10,000 points in this three-dimensional configuration space. So the question we'd like to ask now is, how many potential energy points does one actually need to describe the complete surface of this kind? And this question is best answered by considering quantum scattering calculations as a function of the number of points that you add to the construction of the potential energy surface. So what I've got here is a comparison of the results of the quantum scattering calculations. The black curve here shows the results from the literature by other authors who used the potential energy surface for the system that's based on 8,700 potential energy calculations fitted with some procedure. So our method shows that you can get the red curve with only 30 points used to build a Gaussian process model of the potential energy surface. So this just shows that Gaussian processes can be used as a very efficient surrogate models of the solution to the Schrödinger equation. Furthermore, Gaussian processes, they may also have extrapolation power, as I will illustrate by my next example. To illustrate this, I'm going to consider a problem for extrapolation in the Hamiltonian parameter space. I'm going to consider a complex quantum system for which I know something in one part of the Hamiltonian parameter space, and I'm going to ask my machine learning model to predict the properties of the system in some other parts of the Hamiltonian parameter space. Now, as you move through the Hamiltonian parameter space for complex systems, a lot of interesting things may happen, like you could have quantum phase transitions, for example. So one of the questions that we wanted to ask in this work was whether you can, for a complex system that has multiple quantum phases, whether you can use the known information about the properties of the system in one of the phases in order to predict the locations of the phase transitions, as well as the properties of the system in the other phases. To illustrate that this is indeed feasible, I'm going to show the example of the Heisenberg spin model here. For this model, one can actually use, in the mean field approximation, one can actually calculate the free energy as a function of the magnetization and temperature, and it looks like this. So if you plot the minimum, the location of the minimum of this function as a function of temperature, you're going to get the dashed curve here that is actually the order parameter of the system. And this point here marks the paramagnetic to ferromagnetic transition. So we wanted to see if you could actually use the free energy of the system in one of the phases in order to predict the location of the phase transition and the magnitude of the order parameter in the other phase as a function of temperature. So what's shown on this plot here on the right side are the predictions of the machine learning model, the Gaussian process model, by the symbols. And this model is trained by the free energy in the shaded region of the graph on the right-hand side. And as you can see, the model is capable of extrapolating the order parameter all the way to the phase transition, predicting the location of the phase transition, as well as predicting the order parameter deep into the other phase. Let me now go to the problem of central importance to this session, that is molecule-molecule collisions in a magnetic field. As you know, there are two types of molecular collisions particularly important for the field of cold molecules. That is good collisions, that are collisions that preserve the quantum states of molecules in a trap, These collisions are needed for thermalization and reducing the temperature of molecular ensembles. And then there are bad collisions that are collisions that drive molecules out of the trap. So it's very important for the experiments with cold molecules to be able to predict the relative probability of good collisions and bad collisions. Unfortunately, like I said at the beginning of my talk, it's very difficult, if not impossible, to predict the probability of such collisions, mainly because of the uncertainties in the potential energy surfaces that describe the intermolecular interactions. So what you want to be able to do when you develop theory of molecular collisions for cold molecule experiments, you want to be able to predict the probabilities of the cross-sections of elastic scattering and inelastic scattering with error bars that account for the uncertainties in the potential energy surfaces. So one way to obtain these error bars is to average over variations of the potential energy surfaces. But in most of the previous work, this has been done simply by scaling the potential energy surfaces with a single scalar factor. However, this does not account for errors in the anisotropy of the interactions and many other subtle details that are reflected in the uncertainty of the potential energy surfaces. What is required is the analysis, rigorous analysis, non-ambiguous analysis of the scattering observables as functions of both the strength and topology of the potential energy surfaces that describe intermolecular interactions. And this is particularly important for polyatomic molecules, large molecules. So if you want to be able to analyze the errors of the quantum dynamics calculations associated with uncertainties in the potential energy surfaces that describe the intermolecular interactions, you want to have a method that gives you the variation of the dynamical observables with the different parts of the interactions that describe the different parts of the potential surfaces. However, this is a very difficult task because even for simple systems, potential energy surfaces are parameterized by tens of parameters. And it's simply impossible to compute the dynamical observables as functions of all of the potential energy surface parameters. But we have this approach of ours where we have an observable that's calculated from a machine learning model that already can be used to describe the dependence on the potential energy surface in all possible ways. So this approach, I would argue, is particularly useful for these sort of applications. Consider, for example, the interaction between two complex molecules at a low temperature. As the molecules come together, they will form a long-lived collision complex, and the lifetime of such collision complexes is going to have very important consequences on the experimental observables. So one would want to predict these sort of lifetimes, like I said, with error bars that account for the uncertainties in the potential energy surfaces. And our approach is particularly suitable for that because our approach can formulate the lifetimes, the observables, as functions, as explicit functions of the potential energy surfaces that could be varied in all possible ways to produce predictions of this sort with error bars accounting for all possible variations of the potential energy surfaces. Let me conclude my talk by considering another problem, another application of our approach to enhancing quantum dynamics calculations. See, quantum dynamics calculations for complex systems are difficult. Such calculations must always rely on approximations. So the question I would like to ask now is whether the results of approximate quantum calculations can be corrected by machine learning. And this is the question that we addressed in this paper. The algorithm that we developed in this work is as follows. You would begin by calculating both approximate and rigorous results for some quantum transitions. And then you would build Gaussian process models with multiple outputs that describe the approximate and rigorous results thus obtained simultaneously. And then, I guess the goal is to make a prediction, an accurate prediction for some other quantum transition for which rigorous quantum calculations are not possible. So you would calculate the results for this transition using the approximate approach, and then you would use the Gaussian process models built in step 2 to correct the approximate results. This slide here shows how well this works. I've got here a series of curves for different transitions in molecule-molecule collisions. These are the cross-sections as functions of the collision energy. And the dashed curves are the results of the coupled state calculations, the approximate coupled state calculations, while the solid lines are the results of the rigorous closed coupling calculations. And it's important to note that the numerical difficulty, the numerical effort of the closed coupling calculations, the solid lines, is orders of magnitude larger than the difficulty of the calculations represented by the dashed curves. The symbols here are the predictions of the machine learning models that are trained by a combination of approximate results and rigorous results for a different set of molecular transitions. So this is very important. So the solid lines shown here are not used to train the machine learning models represented by the symbols. The machine learning models are trained by a combination of the approximate and rigorous results for other transitions, not shown here. And as you can see, the machine learning models that's built, they follow the solid curves fairly well. And more importantly, they can also extrapolate to beyond the energy interval represented by the rigorous calculations. There are no rigorous closed coupling results at energies above 1,000 wave numbers. So this graph shows here that it is feasible to build machine learning models that are capable of learning correlations between approximate quantum dynamics calculations and the results of rigorous quantum dynamics calculations in order to correct the results of approximate quantum dynamics calculations for transitions that cannot be modeled with rigorous quantum dynamics. I would like to emphasize that we're exploiting here the power of Gaussian processes to capture correlations. And in this particular case, we're designing a more sophisticated version of Gaussian processes that I described earlier in the talk, in particular Gaussian processes with multiple outputs. And the correlations that are learned by the machine learning models in this case are both between inputs into the machine learning model as well as between the outputs. The other point I would like to make is that this approach does not rely on the accuracy of the approximate calculations. Like in this particular example, it may appear that the coupled states approximate calculations are already doing a pretty good job, but we have verified this, and this was shown in a paper that's cited here, that the accuracy of the machine learning predictions is actually, it doesn't rely on the accuracy of the approximate calculations. So this brings me to my conclusions. So what I've tried to tell you today is that we have developed an approach that allows us to explore the sensitivity of quantum observables to the parameters that define the Hamiltonian, most notably the interaction potentials and their errors. This approach also allows us to solve inverse quantum problems and extrapolate solutions of complex quantum equations, as well as to enhance the accuracy of the approximate dynamical calculations. So I wanted to conclude by showing you a list of some of our publications that describe what I told you today in more detail. And the main reason to show this is to actually acknowledge the people who have done most of this work. So the most important people are Jie Tsui, Rodrigo Vargas, and Jun Dai, the graduate students in my group. If you have any questions, feel free to reach out. You can find my contact information on this website. We're working on a wide range of problems at the intersection of quantum physics, chemistry, and machine learning. So interested graduate students, potential graduate students are always welcome. Thank you for your attention.
Swayam Prabha, Digital India, Educated India.